Use mathematical induction to prove that 7 to the n minus 1 is divisible by 6 for all n in the natural numbers. So our first step, as always, is our base case. Because we're in the natural numbers, that's when n is equal to 0. When n is equal to 0, we have 7 to the 0 minus 1, which is equal to 0, which is divisible by 6. Because 0 divided by 6 leaves a remainder of 0. So the base case holds. Second step is our assumption when n is equal to k. Must write the word assume. So we're going to assume that 7 to the k minus 1 is divisible by 6. And that means that 7 to the k minus 1 is equal to 6a for some value of a in the natural numbers. We don't know what that value of a is, but that's what we're assuming. Step 3, our inductive step, when n is equal to k plus 1. What we want to show is that 7 to the k plus 1 minus 1 is equal to 6b for some b in the natural numbers. So we're trying to show that 7 to the k minus 1 is also divisible by 6. Starting with our left-hand side, we have 7 to the k plus 1. Well, we can use laws of indices to split that into 7 to the k times 7 to the 1, which is just 7 times 7 to the k. And now we need to make our substitution. Well, our substitution in this case is a rearrangement of this. We're going to rearrange this into the form 7k equals 6a plus 1. Because now what we can do is replace 7k with 6a plus 1. We can expand this to get 42a plus 7 minus 1, which is 42a plus 6, which factorizes to 6 lots of 7a plus 1, which is of the form 6b, which was our right-hand side. So we have shown that 7 to the k plus 1 minus 1 is divisible by 6, provided we can make that substitution. That's our process for the inductive step. So now we go on to step 4, which is our conclusion. And in our conclusion, we state, as we always do, that hence, by mathematical induction, since the statement holds for n equals 0, and if it holds for n equals k, then it also holds for n equals k plus 1, it must be true for all n in the natural numbers.